Yeah, 5 minutes. Yeah, I actually. Yeah, 24 minutes. Was it now? So are you going to be positive? Like picked up never left. It's like that's just like the most casual. Yeah. It's like last year. It's good if you just too long, it can be so.
Hi everybody. For those of you that don't know me, I am the president of Titan Rover. And I am here to explain to you why you should consider this for one of your senior projects. So first, what is Titan Rover? So we are a student-led multidisciplinary team that designs, builds, and competes in the University Rover Challenge. The University Rover Challenge is a competition at the end of May each year, where we go to build a rover, and it's always sponsored by companies like NASA, JPL, any big company that is involved in space has basically sponsored this competition. So we develop a rover capable of competing in simulated Mars exploration tasks, including scientific research, robotics, and then mobility design. So why Titan Rover? It's an opportunity to work on innovative robotic designs, gain hands-on experience that integrates classroom knowledge, and then build a rover with real-world applications for space exploration. So we are a multidisciplinary team. So all of you guys are mechanical engineers. So I will just touch on the other ones. But so as a mechanical engineer, you would be focusing on structural design, mobility systems, mechanical robotics, and then science mechanisms that are capable of collecting dirt samples to analyze for Mars. So part of the design, since we are majority robotics, you have to work closely with computer scientists, electrical engineers and computer engineers that make up the controls department, which focuses on the software and hardware behind the entire rover. This includes both the mechanical systems plus an autonomous navigation and UI-based control station. And then we have the natural science department, which is kind of cool. You get to work with biology, geology, and chemistry majors to design an experiment that proves there's life on Mars. And then the business department is responsible for any financial management, marketing, and outreach efforts for Titan rover. So why mechanical engineering is so crucial to our project? So as mechanical engineers, you will play a pivotal role in ensuring the rover is robust, functional, and capable of navigating harsh terrains and completing complex tasks. The key focuses we have are chassis design, suspension systems, wheel design, robotics arms, and then a science mechanism. So first, the chassis. When you think of a chassis, you think of cars. But we build a chassis that forms the frame of the rover and supports all other subsystems, including all housing for our electrical stuff. So ensuring rigidity and durability while minimizing weight, designing for extreme temperatures and terrain, incorporating modularity for easy integration with other systems. So we do have a very low weight limit. So the chassis needs to be light because it is one of the biggest things. So we need to make sure that it's light, but still strong enough. And then also at the competition, the temperatures can go up to 100 degrees. So we need to make sure there's good enough ventilation for all electrical. Some of the things that you can use your class skills for are structural analysis, CAD modeling, and then material selection. So a lot of the mobility system uses FEA, finite element analysis, that actually Dr. Tran teaches last semester, to figure all of this out. So then our suspension system. Again, when you think suspension, you think cars. But suspension is very crucial for us because we are climbing things like rocks. So the suspension system allows the rover to handle uneven, rocky, and unpredictable terrains, just like the Mars surface. So the challenges are balancing stability and shock absorption, developing a system that can handle the rover's weight while maintaining mobility, and then managing energy consumption and reliability under pressure. Some other skills from your classes that get you to this point are kinematics and dynamics, structural integrity testing, because again, it is holding the entire weight of the system, and then suspension design and simulations. With the kinematics of the suspension, you are able to put it through simulations to see where it will land when you actually get time to build it, just to make sure that it works before you go through all of the machining of actually building it. So wheel design. Because of the weight limits, we actually design our own wheels, because buying them is just, it's way too heavy. So the wheels provide mobility, allowing the rover to traverse a variety of surfaces from soft sands to sharp rocks. Some challenges are designing the wheels that can withstand extreme forces, maximizing traction while minimizing wear and tear, and ensuring flexibility for uneven terrain without compromising structural integrity. Mechanical engineering skills that are involved are material sciences, prototyping and testing. Like I had mentioned for FEA, we can't really do it on the wheels because of the specific type of material we use. So we design many different variations and then we test them. Like last year, in the room that we have a rover, there's a second story. We we printed all of them, and then we dropped them off to the second story to see how they work. Designing optimization for performance. So this is actually the system that I work on, the robotic arm. So the robotic arm is used for picking up and delivering objects, all while traversing terrain and increasing difficulty. So not only do we have to pick up an object like a screwdriver or a bucket or anything, we also have to make sure that while the rover is moving over rocks, the hand stays closed and grasped onto that object. So designing a precise, durable, and flexible arm that can operate under the marching conditions, balancing dexterity with strength, because the more the dexterity, the less strength it can involve, and then the ensuring smooth communication and control for remote operation. And then some of the skills that you can use from your class are robotics design from kinematics. Like this is mentioned, you are able to do like kinematic simulations on the entire arm, actuators and control systems. So if you want for like your tech electives, mechatronics is a huge input into the robotic arm, and then advanced kinematic modeling. So what we do once we design the arm and the kinematics, we work with controls to do inverse kinematics. So when they have it on the base station, it can be mapped out and they know exactly where the arm will move to. So the science mechanism. When you think of Mars rovers and like Curiosity from JPL, the main reason they send a rover to Mars is to prove that there is life. So our science system simulates that. The science mechanism will be used to collect dirt and soil samples to search for signs of life. So the challenges are designing a system that can handle soil extraction, preservation, and transport in a limited environment, ensuring the science mechanism can operate autonomously and function in harsh conditions. Our main goal this year, for at least controls wise, is once we have a written out experiment, we want it to happen autonomously, meaning instead of pressing a button, collecting the dirt, pressing another button to analyze it, and then so on, we want to press one button and the entire science experiment happens at once with the correct timing, and everything happening without anything being skipped. So some skills that you'd need is systems engineering, fluid dynamics, if you are using any chemicals or liquids, because you will have to have them moved through tubes or containers. This year we decided to stray from chemicals or liquids and use what is called FAD detection. It uses cameras and a UV light that detects when the UV light is shined on it, it will change the color of anything that is life. And then precision instrumentation. So there's so many precise things that have to do with the science experiment that you will need to know how deep the auger needs to drill into the dirt, how much dirt you need, and you need to figure all of that out and how to get all of that to happen. So why choose Titan rover for your senior design? Real world impact. So to contribute to the development of technology of space exploration, and then diverse hands-on experience. Something that's really cool about this project is once you go into like real world work, you will know how to work with electrical engineers. You will know how to work with biology people. Like you will know how to work in interdisciplinary areas and how to communicate effectively. So, and then industry connections. The University Rover Challenge is so big and it is put on by the Mars Society, where a lot of our alumni just showing up to the competition, like, and looking at that system will get a job opportunity at JPL, NASA, anything that like you can think of. Some companies who aren't sponsored or sponsor the competition will show up anyway and like look at your system, talk to you, and a lot of them leave with jobs. So next season, since this is a senior design, a lot of our lead positions are opening up. So my position as president or project lead, vice president, secretary, chief engineer, chassis lead, suspension lead, wheels lead, robotics lead, and science lead. And then if you want to try something new or fun, you can do any of the business department things. So applications are open from March 17th to April 18th. Executive board and department heads interviews are from April 21st to the 25th. Lead positions interviews are from April 28th to May 2nd, and then if needed, the mechanical senior design team interviews are May 5th through the 9th. So thank you for letting me talk to you guys. If you have any questions, our email is that, our Instagram is that, and if you want to join the Discord, there is a QR code.
Great, thanks, Avery. Yeah, so. Yeah, but I think this class is really good. So I think most everyone here is junior, so I think a lot of people are thinking about their senior design for next year. I'll probably be talking to you a lot about your senior design because you'll probably come to me for advising. But yeah, Rover is a great opportunity. I think the most multidisciplinary of our projects that we have. So yeah, really great opportunity.
Thank you.
Right. Let's bring this back here. How's everyone doing today? Good. Good. Week 3. We are definitely in the swing of things now. Okay.
Really?
Cool. Okay. So plan for today. Last time we met on Thursday, we were talking about second order ODEs. We did kind of a very quick, overview and very quick discussion of the types of equations that you can solve. So I know it was a little bit quick. So today we're going to be going over kind of it again, but we're going to be going over it within the context of an actual application this time. So we're going to be spending most of the day talking about what's called the mass spring damper system, which, probably you've seen before at some point in your educational career, maybe in a math class, maybe in a physics class. But that simple system of a mass spring damper actually can be applied to so many different engineering systems. So if you really understand that system, you really understand its solutions. I think it's something great that you can apply to so many different things, especially for the ME folks in here. So the class you're going to take after this is called vibrations. That's 431. That's vibrations is based almost completely on the mass spring damper. So that's kind of a great thing too. Okay, so let's go ahead and launch into the lecture today. All right, so let's start by saying this is the mass spring damper. And we're studying this within the context of second order ordinary differential equations with constant coefficients. Okay. Of course, that's too long to write, so I'm just going to say with second order ODEs. Okay. So just to kind of refresh your memory, we've been talking about the second order ordinary differential equations. Okay. So these have the form d squared y dx squared plus p dy dx plus qy is equal to 0. Okay. For now, we're setting the right-hand side equal to 0, but if we have time today, we're going to talk about what happens when the right-hand side is not equal to 0. Okay. So specifically, this particular form of the equation has constant coefficients, and so P and Q here are just constant numbers. It's linear, right? So all the y terms only appear in the first order, and it's homogeneous, and so the right-hand side is equal to 0. So lots of terms, lots of ways to describe this, but they all kind of become second nature after a while, right? And so what we went over last time is that the way to solve for solutions to this is to form what's called the characteristic equation. Okay. Remember, the characteristic equation was a polynomial equation, a quadratic equation in particular, that uses the same coefficients of this equation. So, we would form something like, I like using lambda, just because that's how I was taught. Okay, so we have lambda squared plus p lambda plus q is equal to 0. Okay. What we do is we find the roots of this equation, right? So we basically factor it. We either use the quadratic formula, or if you're really good at factoring your head, you can do that as well. Okay, so we call that lambda 1, lambda 2. Okay. And then depending on the nature of these roots, so whether they are whole numbers or real numbers, I should say, whether they're real numbers, whether they are repeated, or whether they're complex conjugates, so you have complex numbers, that changes the nature of your solution. Okay. Right. So I'm not going to summarize all 3 cases here just because that would take too long. We're going to go over it again anyway, but just know that once you find the roots, what your solution looks like depends on what those roots actually do. Okay. So what we're going to do today is we're going to take actually those same 3 situations. So when you have 2 real roots, either you have your repeated root or complex conjugates, and we're going to see how that actually applies to kind of a real world mass spring damper in terms of what you can expect in terms of its physical behavior. Okay. Okay, so let's go over the mass spring damper. So the mass spring damper, like the name implies, has 3 components. And so there is a mass. So the mass usually we just draw as usually just a brick. Okay, so this is our mass. Okay. The actual mass of the mass is given by m. This mass is usually connected to some kind of spring. And I don't know why I did this because I had to draw the spring backwards. Okay, so this is our spring. Okay, the way that we describe the spring is that it has a spring constant K, right? So that spring constant K tells you how strong the spring is. If the spring constant is higher, that means the spring is tougher. It's going to spring back more, more rapidly. Whereas a smaller spring constant means that it's a lot more loose. It's not going to have too much of the restoring force. Okay. Okay. So I think those 2 things are usually pretty easy to kind of visualize just because we've all seen springs, we've all seen masses, right? The other aspect to this is what's called a damper. Okay. Now, the way to represent the damper, there's usually not a good way to kind of represent it, in a drawing because it kind of takes its own form. Okay. But I think the thing that kind of makes the most, I think, physical sense in my mind is to draw what's called like I call this a dash pot. And so you have this kind of plunger that's kind of immersed in some kind of fluid. Okay. It doesn't have to be an open pool like this. I drew the open pool just because, my drawing skills are very limited. So I can't, it's hard for me to illustrate that there's water without drawing the waves. Okay. So this is our damper. Okay. And the idea of the damper is that it's there to kind of, dampen the oscillations or to make it kind of stop, right? And so if you think about kind of water resistance, so, if you've ever kind of been in a bathtub or in a pool, and you try to take your hand, you try to kind of swipe it across the pool like this, there's a lot of resistance there because the water kind of resists your hand, right? You experience the same thing in air, but air is so thin and so light that, air resistance usually you don't really feel. So, water is I think a little bit of a better way to illustrate this. And the way that we kind of characterize or quantify the behavior of the damper is we give it a damping constant B. Okay. Okay. So this is kind of the representation of a mass spring damper. Now, a mass spring damper doesn't have to look like this all the time. Actually, in Avery's presentation today, she talked about this suspension system for the rover. A suspension system is actually a great example of a mass spring damper kind of applied in real life. So, a suspension system obviously doesn't look like this, but it does behave the same, has the same kind of properties. Okay. So what you can expect in this situation, or the way that it kind of moves, is that generally you expect to see that you're going to take the mass, and you're going to displace it by a little bit. Okay, so you're gonna intentionally take the mass and pull it and stretch the spring or compress the spring. Okay, and then what's going to happen from there is that the spring is going to want to try to bring it back to its equilibrium position. Okay. So the spring is what we call it. It applies what's called a restoring force in this situation. Oh, hello, can you guys hear me? Okay, good. Sorry, I think the mic cut out for a bit, so sorry if you guys missed that. Okay. Okay. Anyway, so the way to interpret the mass spring damper is that the mass is going to be displaced, and the spring is going to bring it back to its equilibrium position. Okay. Okay. So when we're first analyzing this system, let's ignore the damper at first, and so we're going to pretend the damper doesn't exist. We're just going to look at the mass spring. Okay. So what's unique about the mass spring damper system is that it actually, its behavior is actually governed by a second order differential equation with constant coefficients that's homogeneous, right? So exactly the kind of equation we've been solving. Okay. Okay, so like I said, we're going to ignore the damper at first. And so if we just look at the mass and spring, okay. Let's see if we can derive a second order equation that's based on just that mass and spring. Okay. Okay. So let's apply the equation for springs, right? So one equation that you've probably learned in a previous class is that when you displace a spring, or when you stretch a spring, the spring is going to apply a force, right? And the equation for that force is given by a formula known as Hooke's law.
But-
Yeah.
My curiosity, but for the damping, is it dependent on the coefficient of drag and viscosity of the liquid?
It is, yes. So that damping constant B that I had above kind of represents that exact, like the coefficient of friction or drag. Yeah. So damping can come from lots of different things. We kind of summarize it as kind of one coefficient B, but that's exactly kind of what it is. Yeah. Mhm. Okay, so Hooke's law for springs is actually quite simple. So what's it basically says that the force that a spring is going to apply is equal to K, which is the spring constant, multiplied by X, which is the displacement. Okay. So this K here is the spring constant. Okay. X here is the displacement. Okay. Oh, one more thing. There's a negative sign, right? Because that spring force is going to be a restoring force. And so whichever direction X is, the spring is going to pull it back. Okay. All right. And so if we draw a free body diagram, and so basically we're saying that the mass is, the only force acting on the mass is going to be the spring force, at least in the X direction. Okay. We're going to ignore gravity because there's nothing going on in the gravity direction. So if we combine this with Newton's second law, so we'll call that Newton 2, right? The sum of the forces on any given object is equal to the mass of the object multiplied by its acceleration, right? Right, so that's just physics 1, right? Force is equal to m. And if the only force that's being acted on this mass is the spring force, we can say that the mass times acceleration is equal to minus K times X, right? And I should probably draw a free body diagram just so you can see, right? So here's our mass, okay? And the only force that's being applied is the force from the spring. So this is Kx in that direction, okay? Right. So free body diagram, sum of the forces, there's only one force being the spring force that has to be equal to the mass times the acceleration, okay? All right, so what do we know about acceleration? So acceleration, right? Acceleration is the derivative of velocity, right? So this is dv dt, right? And what is velocity? Velocity is nothing more than just the derivative of the displacement, right? And so acceleration here is nothing more than just the second order derivative of the displacement. Right? And so if we take this acceleration, if we plug it into our force balance up here, what we're going to obtain from this is a second order differential equation for the displacement of the mass. Okay. All right, and so we have mass times d squared x dt squared is equal to minus K times X, okay? So let's put this in standard form. So let's divide both sides by m. I'm going to move the Kx to the other side of the equation as well, okay? Okay. So you divide by m, we move the Kx over, we get d squared x dt squared plus K over m times X is equal to 0. Right. And so what we obtain from this kind of very simple situation is we have a second order differential equation, right? So our highest order derivative here is 2. The coefficients of this equation are constant because spring constant K is constant. It's in the name, it has to be constant. Mass is a constant as well, okay? And all of it's equal to 0, so it's a homogeneous equation. All right, any questions on how we got this equation from the mass spring? Okay, good. Okay, so we can go ahead and solve this. So let's solve this just like we did before. Okay, so let's form the characteristic equation. Okay, so we have lambda squared plus k over m is equal to 0. Okay, there's no first order derivative here, so there's no lambda term. So just lambda squared plus k over m is equal to 0. Okay. Let's solve for lambda. So this one we don't need to break out the quadratic formula for, because we just take the square root. So if we move km to the other side of the equation, we get lambda squared is equal to minus km, k over m. Okay. We take square root. Okay. On the right hand side, of course, we have square root of a negative number, so that's going to be imaginary. Okay. So lambda is equal to square root k over m times I. Okay. Plus or minus. And so what this tells us is that the roots of our characteristic equation here are complex conjugates. Okay. And in particular, there's no real part here. So we only have the imaginary. And so that means, and so someone asked me this before in the class, and so I know last Thursday when we met, we went kind of through the whole derivation of applying Euler's formula, and how you get complex conjugate roots, how you get sine and cosine. You don't have to go through that entire derivation. And so when you're solving these problems and you see right away that, oh, I have complex conjugate roots, you can just jump straight to the solution and say that it's sine and cosine. Okay, so this tells us that x of t is equal to, now our coefficients are undefined here, so but we have a is equal to a cosine square root of k over m times t plus b sine square root k over m times t. So in other words, our solution looks like sine and cosine, and in fact, there's no decay at all, and so this solution is going to persist, and so this is an oscillation that just goes on forever. Another name for a solution that just oscillates back and forth all the time is called harmonic solution. And so if you graph it out as a function of time, the solution is going to look something like this. And those peaks are going to kind of persist, for long, long times. Okay. So that's what happens when you don't have damping. So when you just have a pure mass and spring, right? Physically, what's happening is that, you're going to pull the mass away from its equilibrium position, and the spring is going to kind of pull it back towards it. But the spring is going to kind of overcompensate. So when the spring kind of pulls it back, it's not able to stop at the equilibrium position, and so it kind of just keeps going beyond. But as it goes beyond, then the restoring force is going to bring it back. And so you have just this constant motion of, the spring just kind of, seesawing kind of back and forth. Okay. So without any damping, right? And so the term that we use for this is called oscillate. So oscillate basically just means that the mass is going to be going back and forth. You've probably seen something like this. It's impossible to have a physical situation without any damping at all. there's always going to be at least some degree of damping, even if it's just something very minor like air resistance. Okay. It's impossible to have I think just I think the idea of a perpetual motion machine is often thrown about kind of in theory. It's impossible to have perpetual motion without, inputting energy to a system. Although, you can have something that gets close. And so you've probably seen a pendulum that kind of just goes back and forth for a long time. Maybe the pendulum is made of some aerodynamic design, which kind of minimizes air resistance. So that may look like something that oscillates endlessly, or at least, kind of approximate that behavior. But there's always going to be some degree of damping. It's impossible for something to oscillate forever. Okay. Okay, so let's go over the damping and kind of what that looks like. Okay. And so the reason I kind of held off on talking about damping, because it's a little bit hard to talk about the role that damping plays without talking about harmonic motion. Okay. And so the kind of the purpose of damping is to kind of prevent endless motion from going. Okay. So most real systems will have damping, and it kind of plays the role of kind of decaying down the oscillation or the magnitudes of the oscillation as time goes on. So I believe we kind of drew a graph of what this looked like at the end of class on Thursday, right? And so with damping, I'll show you kind of how we get the solution in a second, right? So with damping, the solution is going to look something like this. And so we have, maybe the oscillations start very big, but eventually the damping is going to kick in and the oscillations kind of get smaller as time goes on. Okay. And so your oscillations generally get smaller and smaller until they get kind of very, very small that you can't observe. Okay. Okay. And the way damping physically works is that damping will apply an opposing force based on the instantaneous velocity of the mass. And so the idea of damping, this part probably wasn't covered all too much in your previous classes, or maybe it was just covered very lightly. And so, the way we model damping here is kind of the way we model drag or air resistance. So basically, the faster you're going, the more damping or the more air resistance that you're going to feel. Okay? So the force for damping is equal to, we say it's equal to minus B multiplied by the velocity of the mass. Okay, so we have minus B times B. Okay. But we already know, we're going to be solving our differential equation in terms of the displacement of our mass. And so we're going to replace velocity here with the time derivative of the deformation. Okay. So it's minus B times dx dt. Okay. All right, so this is going to add an additional force to our equation, right? And so now our mass has two forces acting on it. So it has the restoring force from the spring, as well as the damping force from the damper. Okay, so let's incorporate. Okay, we're going to incorporate our damping force here into our equations of motion. And so if we, once again, we do a sum of the forces is equal to mass times the acceleration. Okay, now we have two forces, and so we have the damping force minus b dx dt. And we still have our spring force, which is minus k times x. Okay. Okay. So let's go ahead and replace the acceleration there with the second order derivative of the displacement. Okay. This is d squared x dt squared. Okay. Let's move everything to the same side of the equal sign just so we can be consistent here. And we're going to have our full second order equation. So we have m d squared x dt squared plus b dx dt plus kx is equal to 0. All right, and so once again, you can see, even with the damping here, we have a second order linear ordinary differential equation with constant coefficients that's also homogeneous, right? So I'm not going to write out the whole thing. Basically, this is the same kind of equation that we've been solving this whole time. Okay. All right, any questions on how we got this result here? Okay, good. And so just like before, there are going to be 3 scenarios here based on what the roots of our characteristic equation are going to be. Okay, so our solution will take 3 forms depending on the nature of the roots of the characteristic equation. Okay. In fact, let me do this. And so let me go ahead and draw out the characteristic equation. And we're going to use the quadratic formula here to kind of highlight something that's interesting. Okay. What you're eventually going to see is that the nature of the solutions depends on how strong the damping is relative to the other features of the problem. Okay. Okay. And so the characteristic equation here, I'm not even going to bother putting it in standard form. I'm just going to leave it like this, just because I think it makes it a little bit easier to illustrate. Okay. So we have m lambda squared plus b lambda plus k is equal to 0. Okay. So that's our characteristic equation. Okay. So I've taken the coefficients of our differential equation and put it into a quadratic. Okay. All right. So let's use the quadratic formula to find the roots of this equation. Now, of course, we can't actually find the roots because we don't have numbers here, but we can at least get some ideas of what it would look like. Okay. Okay. So lambda 1, lambda 2 is equal to. Okay. And so our quadratic formula is we have minus b, right? It literally is b in this case because we're using the same b for the damping as is the same in the quadratic formula. Okay. Plus or minus. And underneath the radical here, we have b squared minus 4 m times k. Okay. All divided by 2m. All right. So that's what our 2 roots are going to look like. Okay. In particular, I want you to look at the term that's underneath the radical, because that's going to determine what our solution is going to look like. So if we kind of circle this this term right here. Okay. Now, if that term is some positive number, right? And so if b squared minus 4mk is positive, We take some roots with the square root of a positive number, we get positive number. Then we're gonna have two real roots. Okay, so that's one case. Another case is that if that thing under the radical is equal to 0, okay. If it's equal to 0, then we're gonna have a repeated root, because there's no distinction between the roots in that case. And the last case is that if that term underneath the radical is negative, if it's negative, then we're going to have some imaginary number. So we're going to have complex conjugates. Okay. So really the key term here to highlight is that term underneath the radical. Okay. So solution will depend on if this is positive, 0, or negative. Okay, so let's look at each of those cases. Okay, so case 1. So case 1 is b squared minus 4mk is greater than 0. Right, so notice kind of the dichotomy between these two terms. So we have b squared minus 4mk, right? So on one hand, we have one term that's just purely based on the damping, right? So we have b squared, and the other term is mass times the spring constant. Okay, so really the question we're asking is, how strong is the damping compared to the mass and the spring constant system? Okay, so b squared minus 4mk, if that's greater than 0, this is a case that we often call over damping. In other words, there is an excessive amount of damping in the system, present. This also corresponds to the case that we went over last time, where we have two real roots. Okay. And so you kind of make that correlation right now. So when you have two real roots, that means your system is over damped. Okay. Right. And so of course, two real roots, what that means is that your solution here is going to be exponential. Typically, your exponential solution here will be, a decaying exponential, just because all your properties here are generally positive. Okay, and so your solution x of t is going to be equal to a e to the minus lambda 1 t plus b e to the minus lambda 2 t. All right, and so if lambda 1, lambda 2 here are both real numbers, then one thing you should note about this solution is that it's not going to oscillate at all. Okay, that's why we call it over damping. So in this case, the damping is so strong that it's gonna decay any oscillation before they even take place. And so if you draw it out, usually the solution kind of just looks something like this. So no oscillation, you just have exponential decay. Okay. And this is good sometimes. Actually, this is good a lot of the times, because there are a lot of physical systems where you don't want to oscillate. You don't want any vibrations at all. Okay. Case in point, the example we're going to do after this, again, very fitting to what Avery was talking about earlier today, is the suspension system for a car, right? And so your suspension system is very much a mass spring damper, but it's a mass spring damper that's tuned so that the damping is very high, right? Because if you're sitting in your car and you go over a speed bump, and of course, there's people that mod their cars specifically to kind of bounce like this. I'm not talking about that. I'm talking about just regular normal people, right? So for most normal people, when you go over a speed bump, you don't want your car to be, rocking like that, right? You just want it to bump and then just kind of come back down. So you want a situation where you're over damped, so that you don't experience discomfort in your car. Okay. Any questions on over damping? Okay, good. Okay, it's case 2. So case 2 is for when the case wherein b squared minus 4mk equals 0. Okay. So in this case, you can say that damping and the mass and the spring constant are kind of perfectly balanced with each other. Okay. So this situation, we often call critically damped or critical damping. All right, and of course, this corresponds to the case. This was also case 2 of what we discussed last Thursday for when we have a repeated root. Okay. And so if you remember, for the repeated root, in order to get a linearly independent solution, we had to multiply by x, or in this case, we're going to multiply by t. Okay. And so our solution, x of t, is equal to a, let me do it this way. It's going to be a e to the minus lambda t. Okay. There's only one value for lambda because it's a repeated root, right? And our second solution is b with the same exponential, but to make it linearly independent, we actually multiplied by t. And so it's bt e to the minus lambda t. Okay. So once again, for this case, we don't see any sine or cosine. So this one also, no oscillation. And actually, if you graph it, the graph of critical damping actually looks very similar to overdamping, right? Because your solution is kind of dominated by these decaying exponentials. Okay. All right, and so if you draw it out, it's going to look something like this. Okay. So you have a solution here that just kind of decays downwards to 0. Okay. So then what's the difference? So what's the difference between overdamping and underdamping, right? I mean, mathematically, we can see the difference, right? Because with critical damping, or excuse me, the difference between critical damping and overdamping, right? And so mathematically, we can see the difference. With critical damping, we have this extra t in our second solution, okay? But that t, at the end of the day, doesn't do all that much because the exponential decays a lot faster than that t can climb, okay? So the difference is actually very subtle, but it's actually very important for engineering systems where this performance is actually important, okay? For critical damping, the thing that's actually interesting is that, when you have critical damping, the exponential coefficients, the lambdas, are going to be the same on both terms, right? And so what this means is that when you compare a critical damping solution to an over damping solution, the critical damping solution actually decays down a little bit faster. Okay. Now, how much faster it decays down, it depends on how much damping there is, right? But, you know, for most cases, if you compare the two graphs, right? And so if I were to overlay one over the other, you know, the over damping one may look something like this. Right, so in red right here, I have the over damping case, which you can see, you know, still kind of persists for a little bit longer and has a little bit higher values, okay? Whereas the critical damping one kind of goes down to 0 a little bit faster, okay? And why is that? Why is critical damping decaying down a little bit faster? Well, when you have over damping, what can happen sometimes that, you know, usually one of your coefficients or one of your lambda values is going to be very high. And so that part will decay down to 0 completely. But then your other lambda value is going to be a little bit lower. So that smaller solution or that you know lesser solution is actually going to take longer to decay. Whereas if you have a critical damping, both lambda values are equal, and so that kind of shoots down a little bit faster. Okay. So the difference, you know, for a lot of times is usually not that you know, not that important. But if you're designing kind of a very high performance type of system, so let's say you're designing, I don't know, a Miata compared to like a Honda, a Honda, right? You know, if you're designing something that's supposed to be high performance, you know, you're probably going to want to tune your suspension system to be closer to critical damping versus over damping, where, you know, if you're designing a Honda, you're probably designing for comfort. You know, for a sports car, you're designing more for performance. And so these kind of small tweaks kind of matter kind of a bit more in the situation. But visually, mathematically, over damping, critical damping, they look quite similar. Okay, there's just kind of a small difference. All right, any questions on this? Okay. All right, and so the last case, we've kind of already gone over it, but I'll list it again here. So case 3 is for when your quantity b squared minus 4mk is less than 0. Okay. And so in other words, your mass or your spring constant is kind of dominating over the damping. Okay. So this is a case which we call under damping. Okay. Right. And so of course, since that b squared minus 4mk is less than 0, that means, and when we take the square root, we're going to end up with an imaginary number. Okay. And so in this case, you are going to get complex conjugate roots. That means your solution here is going to have sines and cosines. So this is the only case where you do have oscillations in your solution. Okay. Now there is damping present, and so your oscillations are not going to persist until infinity. And so there is going to be a decaying exponential, but there is going to be sine and cosines. Okay. So the general form of the solution is equal to, usually there's some decaying exponential out in front. So that's e to the minus alpha t. Okay. And that's multiplied by a sum of sines and cosines. We have a cosine of omega naught t, okay, plus b sine of omega naught t. Okay. I use new constants here, so I'm using alpha and omega here. Of course, the values of alpha and omega are going to depend on the values for m, k, and b, which are the raw, you know, raw properties of your model. But I just put it there just for convenience. Okay. So your solution is going to oscillate, but eventually those oscillations are going to decay down to 0. Okay, so just like kind of that decaying exponent or that decaying oscillations that we drew earlier. Okay. Any questions on this before we do an example real quick? Okay. All right. So let's do one example just to kind of end the day. Okay. So for this example, let's create a model for an automotive suspension system. So of course, this is going to be a very simplified version of an automotive suspension. We can't model a full thing. There's kind of way too many parts. But at its core, or at its essence, an automotive suspension is nothing more than just a mass spring damper, where the mass, in this case, we're going to assume is all concentrated in the wheel. Okay. So visually, gonna look something like this. So let's assume that this block here, this is going to be the frame of the car, or the chassis of the car. Okay. But we don't care about the chassis in this case, so I'm just going to replace it with a rectangle. Okay. And so from the frame, we're going to have a spring. We're going to have a dash pot as well. Okay. So this right here is a spring. This is a damper. And then to this, we're going to attach it to the tire, which is going to be our mass. Okay. So this is the wheel, or the tire, which is going to be our mass. Okay. Okay, so we can model this, we can model the behavior of the suspension, or in other words, we can model the motion of the wheel in the suspension using our second order ordinary differential equation. All right, so we have m d squared x dt squared plus b dx dt plus kx is equal to 0. Okay. All right, let's actually put some numbers on this one, just because we've been working in symbols kind of this whole time. Okay, so let's say the mass is 12 kgs. Okay. The damping constant in this case is going to be 240. Let's see, what are the units for this? So this should be newtons divided by meters. Newton second over meters. Okay. And the spring constant in this case is 1152 newtons per meter. Okay. We're going to assume everything is an SI. Okay. So first thing you want to see is that if the suspension system had these values here, what you want to determine first, is your solution going to be over damped, critically damped, or under damped? Okay. So that's the first thing we're going to determine. Okay. All right. So in other words, we're going to solve for the general solution to the differential equation. Okay. Typically, for a suspension system, and you have a homework problem in this as well, right? Typically, if you have an underdamped suspension, right? And so if your suspensions don't have strong damping and there's going to be oscillations, usually that's going to be an indication where your suspensions are a little bit worn out and maybe it's time to replace them or get them fixed. Okay. So if your suspensions are underdamped, this is usually not good. Okay. Some under damping is okay, sometimes you don't, even if it pops a second time, sometimes you don't feel it. If it's small enough, but if the damping is really low, then that might be a good time to replace it. Okay. And so, the first question we're going to ask is, are these suspensions in good shape? And do we need to replace them? Okay. That's actually the question that I asked you in problem 3 on the home. So I gave you kind of another car suspension system. I want you to tell me if we need to replace these suspensions or if we can kind of keep them for a bit longer. All right, the other thing we're going to ask is that if this car goes over a speed bump, okay, we want to be able to model the oscillations, or we basically want to model the behavior. And so when you go over a speed bump, basically, we're going to assume that the speed bump is going to cause your tire to kind of shoot upward with the velocity. Basically, we're going to say is that we're going to assume x of 0 is equal to 0, but dx dt, not dx dx, dx dt at t is equal to 0. We're going to say this is going to be equal to 10 meters per second. Okay. All right, so that's the second part of the problem. Okay. So second part of the problem, we're basically going to apply initial conditions. And these initial conditions are meant to model what's going to happen when you go over speed bump. And we're going to see, how that affects the solution. Okay. Okay. Any questions on the setup for the problem or kind of what we're looking to solve? Okay. All right. So let's go ahead and solve it. So let's start with the first one. So to determine whether our suspension is over damped, critically damped, or under damped, we need to solve the characteristic equation. Okay. So we have numbers here, so we can go ahead and plug it in. So our characteristic equation here is 12 lambda squared plus our damping is 240 lambda plus our spring constant is 1152. Okay. All right, so let's compute the roots. So you can compute the roots in one of few ways. And so one way is let's go ahead and just plug it into the quadratic formula. Okay. So we have lambda 1, lambda 2 is equal to minus b. So we have minus 240 plus or minus square root 240 squared minus 4 times 12 times 1152. Okay. All divided by 2 times m, so 2 times 12. Okay. So there's a lot of big numbers there, of course. And so, unless you're very good at doing mental math, you'd probably need a calculator for this. But thankfully, just because I had the magic of foresight and choosing numbers that are nice, the roots here are pretty nice. Okay. So our roots are minus 8 and minus 12. Okay, and so that's of course what you get by evaluating that quadratic form. Okay. So this is good. So the fact that our roots here are both real numbers, and there's no repeat, this means that our suspension here is over damped. Okay. That's good. That means our suspensions are in great shape. They might be in too good shape. But -8, -12, those are pretty close to each other. And so, I would say this is a very healthy suspension. Okay. And so our general solution x of t is equal to a e to the -8 times t plus b e to the -12 times t. All right, any questions on that? Okay. Okay, so now let's take the solution and let's see what happens when we run over a speed bump. And so to simulate that, we're going to apply our initial conditions. Okay. So our initial conditions are x of 0 is equal to 0, right? And so we're going to assume that we start from a resting position, but as soon as we run over the speed bump, it's going to apply initial velocity. Okay. So dx dt, keep doing that, dx dx. Okay. Dx dt at x is equal to 0 is going to be equal to 10 meters per second. Okay, so let's go ahead and apply these conditions here. So first we have is x of 0, right? We're going to plug in x is equal to 0 into both values of t there. Okay. That's going to be equal to a times e to the -8 times 0, which is just 1, plus b times e to the -12 times 0, which is 1. Okay. So you have a plus b is equal to 0. Okay, so that's our first boundary condition. Okay. For a second boundary condition, let's evaluate the derivative. And so if we evaluate the derivative, we have -8a e to the -8t minus 12b e to the -12t. Okay. We evaluate this at t is equal to 0. Okay. We get -8a minus 12b. Okay. Both the exponential terms are going to be equal to 1 because we have exponential of 0. Okay. Okay, so we have -8a minus 12b. And we know that when we apply t is equal to 0 to the derivative, we get 10. Okay. Okay, so these are our two equations. Okay, so we have a plus b is equal to 0, and then -8a minus 12b is equal to 10. Okay, so we have two equations and two unknowns. And just in the interest of time, I'm just going to go ahead and skip to this solution here. But you can solve that system of equations however you want. And so solving this system, we get a is equal to 5/2, and b is equal to -5/2. All right, and so when we put it all together, our final solution here, x of t is equal to 5/2 e to the -8 times t minus 5/2 e to the -12t. Okay. And so we can use that equation there to model, what our vehicle is going to do after we hit the speed. Okay. And if you want to look at the graph really quick, okay, it's going to look something like this. And so generally what you expect after you hit the speed bump, your wheel is going to displace a little bit. Okay. And so that's what we see here. But because of the damping in the system, that displacement just damps down very quickly. And there's no oscillation at all because your suspension is in good shape. All right, any questions on this example here? Okay, all right, so that's all the time we have for today. And so when we come back on Thursday, we're going to talk about non-homogeneous solutions. So what happens if the right-hand side is not equal to. Okay, all right, so thank you guys for coming today. I hope you guys have a good rest of your day. I will see you guys later.
My number here.
Well, I assume that the lambda one, lambda two are real numbers. So I just put the negative there just to emphasize the fact that it's decaying down. So, in reality, you know, lambda one, lambda two are probably going to be naturally negative like this.
Oh, yeah.
I only put the negative there just to emphasize that it's decaying.
Oh, so.
Yeah, but if you're right, but if lambda one, lambda two are already negative right here, you don't apply the negative twice.
Yeah.
So yeah, you can just
All right.
Yeah.
So, wait. How about this? How about this one?
same thing, same thing
Same
here.
thing.
Yeah,
right? Okay.
yeah, I put the negative just to emphasize that it's normally the case.
This is my
Mhm. No problem. Have a good day.